Stoichiometry of limiting reactants. In this lesson, we will see what to do when there are more than one given values. This is equivalent to a question like this. If we have multiple pieces of bread and multiple pieces of cheese, or so many pieces of cheese, if we know both amounts, in other words, we can still figure out how many grilled cheese sandwiches are going to be made, but it's going to be a little bit of a different process than before. We've sort of oversimplified it with our process. We're going to have to add a couple little steps here without really changing any of the overall ideas here. We're just going to have to add a couple of steps. So what do? Well, let's start with the problem. How many grams of carbon dioxide is made from the combustion of 25.0 grams of butane and 40.0 grams of oxygen? Now, if you're paying close attention, you'll realize that this is the same, or it's a very similar question to what we learned stoichiometry on, but we've added one more piece of information. We'll talk about what that is if you don't recognize it already here in a little bit. So go ahead and copy that question down. So the first step, of course, is that you need a reaction, just like before. No changes there. So combustion of butane reaction, butane plus oxygen yields water and carbon dioxide. You've got to balance it. There we go. And I suppose I should wait a second and let you pause until you have that all down. Yada, 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 and go. So the step 2, you got to identify A, what you know, and B, what you don't know. But whoa, but wait. Both. We know both. We have two different things that we know. We got to identify both of them, and both of them are going to be labeled A now. We'll get to the example in a moment, but then of course B doesn't change. B is still trying to identify what you want to know. So what is this both thing? So let's go back to the problem. A is the thing we know. Well, we know 25 grams of butane. That is A. That is our known value. But if you look and continue reading, you'll see that we also know that there are 40 grams of oxygen. So that is also our known A. We have two known values. So how are we going to deal with this in a problem is what we've got to talk about. B is still how much carbon dioxide is made. That's still what we want. That's not changing here. So butane is A, the thing we know, but oxygen is also A, the thing we also know. And carbon dioxide is B, the thing we want to know. So there's our reaction. There is our A. Oh, but there is our A also. I'm going to label them both. We know both of those quantities. And there is our B. So what do we do next? Well, we follow. A lot of this process doesn't really change. It's almost exactly the same process as for a regular stoichiometry problem, except we're going to add one little step at the end, and we're going to actually have to double some things, do some things more than once. So the next step, of course, is to convert both of what you know into reaction units. So nothing big and fancy or different here. We're just going to do what we did before for each thing. So we got to convert it into moles. We got to use N equals G over W, but we've got to do it for both things. So N equals G over W. So let's go. So our first A is butane. We got to find the moles of butane by taking G over W. G is 25.0 divided by the molar mass of 4 carbons and 10 hydrogens, which adds up to 58.0. And just like in the example problem, that comes out to 0.431 moles of butane. But we're not done yet. We've got to do it for the oxygen also. So we've got to do the exact same process, but now we've got to substitute the mass of oxygen, the molar mass of oxygen. Well, the mass of oxygen is given in the problem as 40.0 grams. And the molar mass of oxygen, 2/16, is 32. Again, we do count the subscript when figuring molar mass, but we ignore the coefficient. Meanwhile, I've realized that somehow we missed our 2 here. There should be a 2 here. In this series of slides, that 2 is omitted. So when I hit forward here, it'll go away again, but just realize that should be there, and it will be there when we need it later. So 40 divided by 32.0 down here is 1.25 moles of oxygen. So we have 1.25 moles of oxygen and 0.431 moles of butane. So that's how much we have of each of those things. And so now we go back to what we would normally do. We could use a reaction to determine how many moles of carbon dioxide can be made with each of those known quantities, beaver over armadillo, but we got to do everything twice. Do everything twice, do everything twice, do everything twice. So let's do everything twice. So there's our moles of A for butane, and there's our moles of A for oxygen, and we're going to start from there. There's the formula in the context of the 5 steps, and boom. So let's do this. Let's do butane first. So butane's highlighted there. There's our formula for moles of B. We're going to take moles of A times the coefficient ratio. So moles of A is 0.431. We just calculated that. The coefficient of B is 8. So we're going to take it times 8. We're going to divide it by the coefficient on A, which is 2. So 0.431 times 8 over 2 is 1.72 moles of carbon dioxide, which I believe is the same number we got when we did this problem before. But we're not done yet. We got to do everything twice. We now need to move to the next A. We got to move to the oxygen. So now that we know the moles of B that butane can make, we got to figure the same thing out for what oxygen can do. So oxygen, same formula there. So we're going to start with moles of A, but be careful. We're not going to start with 0.431 this time, because that was the moles of butane. We want the moles of oxygen, which we just calculated as 1.25. We're going to take that times a different coefficient ratio here. Now, it's still going to be B over A, but remember A is changing. So we're going to take it times B, which is still 8, but over A. A for the oxygen is not 2, it is 13. So that's a different coefficient ratio here, and that's going to give us 0.265 moles of carbon dioxide. So, woo! I thought I had a slide here where I circled those. But, there we go, now I do. Isn't that awesome? Wonderful. So, there are enough butane molecules to make 1.72 moles of carbon dioxide, but there's enough oxygen to make 0.265 moles of carbon dioxide. And so, now, we've got to figure out which of those two we proceed with. I'm sorry, which of those two to proceed. And it's just like the grilled cheese sandwiches. If we have enough grilled cheese, if we have enough cheese to make 12 grilled cheese sandwiches, enough bread to make 4 grilled cheese sandwiches, clearly we can only make 4, because once we run out of anything, we're done. The thing that we run out of is limiting how much we can make. That is why it is called the limiting reactant. The smaller amount that can be made is the one by the limiting reactant. Now be careful, it's not necessarily the one that there is less of. You might have a case where you actually have fewer slices of cheese than bread, but the bread will still limit you. For example, let's say that we have 4 slices of cheese and 6 slices of bread. Well, the bread could make 3 sandwiches and the cheese could make 4. Even though there's more cheese, more moles, if you will, of cheese, of bread, more moles, more slices of bread, you're going to run out of them first because you use them up at a higher rate. Look at these coefficients. These coefficients sort of tell you the rate at which these things are used. Notice that we start out with 1.25 moles of the oxygen, and we start out with 0.431 moles of the butane. So you might say, well, we're going to run out of butane first because there's like almost 3 times as many oxygen molecules as butane. But the reason that's not true is because of these coefficients. You use 13 oxygens for every 2. It's used up at a rate of 6.5 times as much. So the point of all this is you've got to wait until step 4. Use step 4 to determine how many moles of B can be made before you determine which of the 2 answers to proceed with. If you do it at step 3, if you've done it at step 3 in this last problem, we would have thought that the limiting reactant was butane, because it's a smaller number than 1.25, but we would have been wrong, because as we see, the oxygen actually produces fewer moles of carbon dioxide than the butane, because the oxygen gets used at a much greater rate. So you must proceed through step 4 before you compare. So what we do at this point, now that we've sort of compared what the amounts of the different things can be made. To step 5, we're going to answer the question. But we're going to answer the question proceeding using the smaller of those two numbers. The smaller of those two numbers. So, because whichever one is smaller tells you how much you can actually make. Whichever one is smaller is the one tells you how many you can actually make. If you have enough bread to make 12 and enough cheese to make 6, you can really only make 6 because you're going to run out of cheese first. So the one you run out of first limits how much of the product you can make, which is why we call it the limiting reactant. The one you run out of first, the one that produces a smaller number of moles of B, that is called the limiting reactant, which is why we call this a limiting reactant problem. And the way that you do it is, like we said a minute ago, you find moles of B for each A, and then proceed using the smaller of the two. So back here, our 2 moles of B were 1.72 moles of carbon dioxide from the butane and 0.265 moles of carbon dioxide from the oxygen. The smaller of those two is the one that is true. So we can eliminate the bigger one and proceed with the smaller one. We can throw 1.72 moles of carbon dioxide out the window. We can pretend that we never saw it, just scribble it off, and proceed with the 0.265. That is our true moles of B, and that's what we're going to finish the problem with. So how do we finish it? This is the way we would always finish. 0.265 moles of carbon dioxide will be made, which is N times W will give us G, and that's 11.7 grams of carbon dioxide. So the answer is 11.7 grams of carbon dioxide. And that is how you do a limiting reactant problem.